All right, happy Tuesday, everyone. This is our official second class meeting. Today, we're going to be going over chapter 2, sections 1 and 2, and then chapters 1 to 3. That's the goal for today's lecture. So we want to start off by downloading these items. And tomorrow, I'm going to be uploading new content for what's going to be covered for next week, meeting number 3. Okay, so what is due today? What is due today is your discussion post number 2, along with your homeworks. And remember, on June 6th, that's going to be your first quiz. Alrighty, any questions from that? All right, so with no further ado, I am going to go ahead and share my iPad. And this is the first chapter 2, section 1. I'm going to be going over this section, of course. This section talks about exploring data with tables and graphs. So let's talk about that. So we're going to be talking about frequency distribution. What is a frequency distribution? What is it used for? It's used for organizing and summarizing data. So the key concept, again, is to organize and summarize data. A frequency distribution helps us to understand the nature of distribution of a data set. So when we're given a data set, what do we do with that data? We organize it in a way that is going to be easier for the reader to obviously analyze and to observe. Okay. So in a frequency distribution, how do we organize the data? We actually partition the data, calling them classes. So for each data that we're given, we're going to separate the data in different classes. These are categories with the number of frequency and the data values that each of them are shown. Okay, we're going to see an example of that today. So each class has a lower class limit, an upper class limit, and a boundary. So when we partition, let's say I give you 12 different data values, you're going to partition those data values in classes. Within those classes, we have lower class limits, which are represented by the smallest number that can belong to each of the different classes. Upper limits are the larger numbers that can belong to each different class. And the boundaries are the numbers used to separate the classes without gaps created by class limits. Your class boundaries will be the numbers that are going to be seen as decimals because it's a number to separate the class. So if it's a class that's divided by a quantity of 1, then maybe a 0.9, a 0.5, a decimal will show up on a class boundary. So let's write that down. This is where usually a decimal number will show up. And that is because we are partitioning our classes. Any questions with any definitions so far? Any content? Okay, remember, I am looking at the chat in case you have any questions. We have midpoints. The midpoint is actually the middle of the classes. So you're going to actually take the average. So take the mean between the class. Okay, so you're going to add the lower class plus the upper class. So L, lower class plus upper class divided by 2 in the same class. So for example, we have 5 classes. Well, we have 5 midpoints. And we're going to have 5 boundary points. And the class width is actually defined by the difference between 2 consecutive lower class limits. So if let's say that I'm giving an example, I have 1 through, let's say 4, and then 5 through 8, and then 9 through, well, 12. What would be, let's say, so for example, I have this is 3 classes. So I have class 1, class 2, class 3, so 3 classes. The class width is actually the difference between 5 and 1. So 5 minus 1 is 4. So the distance, the width is 4 because 5 minus 1 is 4, 9 minus 5 is 4. Okay. I haven't taken attendance. I usually take attendance, Kiana, when I ask for your name at the end of the class. But thanks for that. All right, so your class width would be 4 if I'm given this example. Your upper class and your lower class, well, my lower class, I will have 1, 5, and 9. Those are the lower class, 1, 5, and 9. My upper class would be what? What are the answers? What would be my upper class? Put your answers on the chat. If my lower class is 1, 5, 9, what are my upper classes? Any ideas? What would be my upper class? So 1, 5, 9, those are my lower. Thank you, Natalia. Thank you, Joel. Thank you, Luis, would be 4, 8, and 12, exactly. Now, those are my upper 4, 8, and 12. Now, if I want to find the midpoint over here, the midpoint would be the average between the two. So I would do 1 plus 4 over 2. That'd be the first, 5 over 2, or 2.5. And then I have 5 plus 8 divided by 2. That would be my second. 5 plus 8 over 2, that would be 6.5. And then what would be the other one? It would be 10.5. How do I get 10.5? Well, 9 plus 12 is 21 divided by 2, 10.5. Those are called the midpoints. The boundary points would be between a 4 and a 5. Well, we could have 4.9, and then we would have 8.9, and we would have 0.9. So the one before this. So it's 0.9, 4.9, 8.9, and then we would have 12.9. So see, the distance is still 4. So here will be my boundary points. Those are called the boundary points. So that is a quick example. We're going to see, of course, another one. How do we construct the procedure for constructing a frequency distribution table? We are going to be selecting the number of classes, usually between 5 and 20. So between 5 and 20 classes we're going to have. We're going to be calculating. Sometimes I will not know what the class width is. I do not know what it is. So I'm going to calculate it by using a formula. I'm going to take the maximum data value minus the minimum data value divided by the number of classes. We usually want to round this result because sometimes this answer will be a decimal answer. That's not going to help us a lot. So depending on the data values that we're given, that's what we're going to round up. We're going to round it to a convenient number. Okay, so it's the maximum data minus the minimum data divided by the number of classes. So then we're going to choose a value for the first lower class limit by using either the minimum value or a convenient. It might, probably the value that we pick might not be in the data, but it's a convenient number to start off our data. Does that make sense? Is that, we'll see an example and then everything's going to kind of come into play. We're going to be using the first lower class limit and the class width. And then we're going to list all of the lower class limits. We're going to list the lower class limits in a vertical column. So we're going to be creating something like this. So on this side, we're going to be having the number of classes. So I'm going to have 1 class, 2 class, 3 class, however classes we have. And then next to it, we're going to see how many of those data values are in there. So this one's going to be a tally. We're going to tally up those values. That's what this is saying. We're going to take each individual value and put them on a tally in the appropriate class. And then we're going to count the tallies to get the frequency. Let's look at this example. we're going to assume, so this is given to us, this is the data value that we're given. Using the data to commute an LA in table 2-1 from the chapter problem of the above procedure to construct a frequency distribution in table A-2. So they're already telling us how many classes they want. They want 7 classes. So what we know is that to find the class width, it's going to be the maximum value minus the minimum value divided by the number of classes. That's going to give us an approximation. So if we look at the data, we want to find, okay, well, who's the minimum and who's the maximum? So what is the maximum value? Well, I see a 75, I see a 90. Is there something more than 90? Do you? I don't think so. I don't see a 100, a 90 and something. I just see 90. I think that's the lowest. Sorry, that's the greatest number. So the max of the value is 90. The minimum value is, I see a 5. Is there something less than 5? So I saw that the greatest one was a 90. I see a 5. Is there any value less than 5? I don't think so. 5 is the lowest. Okay, the minimum value is 5. And we know that the number of classes that they want is 7. So what we're going to do is going to do 90 minus 5 divided by 7. We get 85 over 7. What happens when we divide 85 over 7? What do we get? Do we get what? So 85 divided by 7 is what? It's roughly 12.14. So what I'm going to do is I'm going to round, because I want 7 classes, not 8 classes. You're going to say, oh, I'm going to round down to 10 because I see 10s. Well, that's a smart guess. However, you want to have 7 classes. So I'm actually going to round to 15. And you're going to say, well, how are you going to round from 12 to 15? Well, I'm going to round it to 15 because I have zeros and because I have 5s. I don't want to do 13 because look, see how they're not divisible? The 60, the 5, those are not divisible. So I'm going to round the class width of 15. So if my class width is 15, so we determined that the class width is 15. So notice it's from 0 to 15 to 30 to 45 to 60 to 75 to 90. We start at 0. We will not start at 1. Okay, because if we would start at 1, then it would have to be 1, 16, and then so on and so forth. Does that make sense? Because we always have to make this with 15. That's what we rounded off. So we're going to be selecting values from 0 to 14 and then 15 to 29, 30 to 44. So once we predetermine the class, the upper and the lower, the upper and the lower, sorry, the lower, the upper, the lower, the upper, the lower, the upper. And then we're getting these numbers and we're going to tally them up and we're going to put the frequency. So the time in reality, this time is representing your classes. So a category from 0 to 14 minutes, from 15 to 29 minutes, from 30 to 44 minutes. Any questions on how I got this? That's the first question. Some frequency distributions might look, there's an 18, does that matter? No, that does not matter because it's going to fall into the one of the categories. So because most of the numbers, most of them are 5s and 20s or 10s. We want to round up to 15. We don't want to round down to 12 because that would make it more than 7 classes. So we always want to round up. We want to make sure that we follow the category. So I could have picked, let's say that, notice that 0 is not on my data, but 5 is. So what I could do instead is, okay, I want 1 through 15, then I would be 16 through. So see how the 1 and the 16 minus 1 is a 15. So I could have done, I would start like this instead. 30 and then 31 to, here, I would just, so from here to here, notice that is also 15. Same thing, folks. So I could have done this or this. So the table is choosing from 0 to 14 because it's nicer, it's easier for us. Okay. But again, there's more than one right answer. Me and you can have different types of frequency distributions depending on what we're given. So the next part, the frequency is just counting. So how many from 0 to 14 do you see on your data? And this is where you start counting. So do I see a 0? No. I see a 5. I see an 8. Up to 14, I see another 10, and I'm going to count. Remember, I'm not counting 15. I'm counting everything less than 14. So I think that's it. 1, 2, 3, 4, 5, 6. That's the 6 that I have right here. And then 15 to 29. Now I'm looking at the data and I'm going to use orange color. Data values from 15 to 29. So I see 1, 2, 3, 4, not 30, 5, 6, 18 works. Let's look over here. I see another 15, not a 20, another 15. And I think that's it. Let's count the oranges. And remember, I'm using colors because you can get lost in the data. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, it's all the way to 29. So I can continue counting. I can count the 20s, count the 20, count the 20, count the 20. Not 30. I see a 25. See how you missed some of these? So again, then I have another 25 and another 25. See how they sneak in? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I'm missing 2. Do you guys know where they are? From 15 to 29? I might be missing. Did I miscount it? Not 30. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Now I counted 17. Did I miscount? There's a 25 next to the 8. Next to the 8. Which 8? This one. Oh, right here. Thank you. See how you get lost? That's why I say, thank you, Dustin. Thank you, Natalia. So then there is 18 of those. So that's how we see this 18. And then same 30 to 44. Well, how many of those do you see? I'm going to use in black. So 1 all the way to 44, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Let's see. See how they get lost? I see only 11 and it's all the way to 44. Is there anyone else? I see a 40. I see a 40. There they are. Do I see another 40 right here? There's another 40 right there. So let's count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There it is. And there's a 14. So I have 14 blacks. So do you guys get the idea? 45 to 59. Then you count them. There's 5 of those. 60 to 74. There's 5 of those. And then when I add the frequency, it's going to give me the total values that I have. So in this case, I have 6 plus 18 plus 4 plus 5 plus 5 plus 1 plus 1. That's all the data values that I have in there. So if I sum them, 6, and then you guys will have a calculator, 18 plus 14 plus 5 plus 5 plus 2, there's 50 in total. Right? So the number of total values in there is 50. Okay. So this is called a frequency distribution table. On this side, we have the number of classes. So that corresponds to 7. 1, 2, 3, 4, 5, 6, 7 classes. Okay. So then there it is. We found this value 90 minus, there should be a minus right here, 90 minus 5, 12.5. 15 is a convenient number. The lowest would be from 0 because we have a value of 5. So we can have from 0 to 5. And then we have, of course, our class width. So from 0 to 15 to 30 to 45 to see how nice these are. These are your lower class limits. And then those are your upper class limits. So they have there your lower and then your upper, and then this is the frequency. Now, this is called your frequency distribution. Just by the data, you separated them into classes, upper class, lower class. Now, and this is the frequency. Now we know that the total value of the frequency, if I add, the total is 50. Now there is an additional part called relative frequency. A relative frequency is pretty much just adding another column right here and calling this the relative. And make sure, and that's going to be, let me add this row and this column. It's actually going to be a percent. So let me get rid of this. So for the first one is actually 6 out of your total 50, and we're going to calculate a percent. And then 18 out of 50. Why out of 50? Because that is your total. We want to see this class limit or this class width has how much percent of the total. And then this is going to be 14 out of 50. We're going to rank it 5 out of 50. We know that this is 0.10, okay, or 10%. So we can put it as a decimal, and then because this is 1/10, this is another 1/10. This is 1/50, 1/50. Okay. So this is going to be 2%, 0.02, 0.02, or 2%. And then we can calculate the top by just our calculator. 14 divided by 50 is 28% or 0.28, 28%. 18 out of 50, and then again, you're given a calculator, will be 30.36 or 36%. And then 6 out of 50 will be 12% or 0.12. What happens if I add all of these percentages? I should get 100%. That is called the relative frequency. So I'm going to scroll down. It's going to, so for each class frequency, you're going to be replacing it for the relative. Okay. So there we have it. So the relative frequency will be 12%, 36, 28. Remember, how did I get those values? Right here. 6, so the frequency divided by the total, the frequency divided by the total, the frequency, and pretty much all they did, they replaced the frequency, so they don't have them together. They just either have the frequency distribution or the relative frequency distribution. Any questions on this part? Okay, I know it's a lot of information. I hope that you guys are taking notes as we're walking along, as we're reviewing the content. Hopefully you guys already saw this before. You already seen this before. This is not the first time. Hopefully you guys reviewed your notes. So that is your relative frequency. There it is. It's the relative frequency distribution or a percentage. So it can be called a relative frequency distribution or a percentage frequency distribution. They're interchangeable. Okay, they mean the same thing. What are the comparisons? When you are combining 2 or more relative frequency distributions in one table, it makes the comparison data much easier. So what we can tell is what is the majority? So it's going to take more people, 36% of the population of the data that we're given, between 15 to 29 minutes to commute. So that is where we see the peak in the commuting. Between 15, it's going to usually take you from 15 to 29 minutes to be commuting in LA. So again, it's allowing you to organize the data in a way that it's more efficient for you to kind of categorize and identify what is going on, what is the context of the problem. Okay. Any questions so far? Okay. So we will have a break in an hour or so, an hour and a half. I just want to, I'm going to be drinking water. So sorry about that. I know if you guys need to step out, use the restroom or whatnot, that's fine. So let's look at this. Now, in this case, they are not telling us what the data values are, but they're giving us the relative frequency. So the tables on this example shows us the relative frequency distributions for 1,000 commute times, okay? So this is the table that we're given from 0 to 150 minutes, assuming, and this is separated by percentages, the relative percentages between them, and they're 1,000 commute times. So they're giving us 1,000 data values. Notice that they're not going to give us the table with 1,000 data values and then we're going to be separating. No, so there's a computer that does it for us. But the whole purpose is just to look at the representation. And then we're going to be looking at the peaks of each table. So there's a peak here. What about the minimum? We want to look at the times where they kind of match. And where is the maximum of them? So what is the piece of data that I want to take out from this? So we're going to see that Boise, it takes more, it takes from 15 to 29 minutes to commute, whereas it's going to take New York 24.8% versus 17%. So notice that the commuting times are longer in New York than Boise. Okay, so normally there's not going to be a lot of minutes for them during 105 to 1 between an hour and 45, an hour and 30 minutes, or 2 hours here. 120 minutes is 2 hours. Anything between, so this is already a 1 hour and 30 minutes. Anything past that, it's pretty unrealistic. But look at this, look at the New York. There is still a chance that it might take more than 2 hours and 30 minutes a commute in New York, whereas Boise, you won't have it. So because of the different sizes of the two cities, we might expect the commute times to be very different. By comparing the relative frequencies, we see that there are major differences, and that's what we want to look at. The Boise commutes appears to be lower than the New York times. So again, look at this, look at your averages, what we have on this side, what do we have on this side? Looking at the percentages, where do they become? Okay, so these results are not surprising, and they're not very eye-catching, because we might expect that in a city that is very popular like New York, definitely the commute times will be longer than the other city. What is a cumulative frequency? So this one is actually a sum between them. So here we start with adding. How did we get from this to this? Well, we actually look at the first parts. It's cumulative. So I'm going to go back to this data, to the first. I'm going to go back to the frequency. Okay. And I'm going to get rid of this. And now, instead of putting relative, I'm going to put cumulative. It's going to be a cumulative distribution. So how do I get a cumulative? And it's actually a sum. And you already know what the sum is. We know that the total is 50. But for a table, how does that look like? A cumulative distribution, you begin with bringing the 6 That will always be your starting point. And then you add diagonally. So 6 plus 18 will give me what? 24. And then I have 24 plus 14 will give me 38. 38 plus 5 will give me what? 40 what? So what are we doing? 6 plus 18, 24, 24 plus 14, 38. 38 plus 5 will give me what? 43? Yeah? 43. Oh, this should go over here. 43 plus 5 will give me 48. 48 plus 1 would be 49. 49 plus 1 is 50. Oh, look. That's my tally. Right? And that's exactly what I get. So I'm adding the 6 and then the 18 to be the next row, and then the next row, and then the next row, and then the next row. So this, look at the values, match exactly what we have down here. And that is called a cumulative distribution. 6, 24, 38, 43, 48, 49, and 50. Less than 15, so this is the one from 0 to 14. Less than 30, 15 to 29. This one is less than 45, which belongs to 30 to 44. Less than 60 represents the 45 all the way to 59, and then so on and so forth. Okay, and then here we have, of course, our 60 to our 85, so on and so forth. Does that make sense, everyone? Okay. So if we have the values 60 to 74, let me bring this. So this, it means the same thing, okay? And then we have, of course, the 75. And then we add our 15, 89. And then we have our 90 to our 104. So all of these match exactly. So just the wording changes in reality. That's all that happens. Any questions on cumulative frequency? So in statistics, we are often interested in determining whether the data have a normal distribution. The frequencies start low, then they increase 1 or 2 high frequencies, and then they decrease to a low frequency. The distribution is approximately symmetric. Frequencies preceding the maximum frequency should be roughly a mirror image of those following a frequency, a maximum frequency. So for example, it starts low and then it will hit a peak and then it's going to go low again. So for us in this course, we're going to be studying, and let me make this big and better. A graph that looks like this. This is called a normal distribution. So that starts small, but then it's going to reach a peak, and then you're going to have things that look like mirrors. So this side should look a lot like this side, and then you should have a midpoint, a peak. And that peak represents the mean of this normal distribution. So what this course is about is actually studying a normal curve that looks like this, a normal distribution. In a perfect statistics class, everything will lie in a normal distribution. That is not the case. That's why we do higher order statistics. But in this class, all we're going to be doing is focusing on this normal curve. And as we progress, you'll learn about that. Okay. So let's look at this one. This is the example that we had. Be careful. This is not the same data as what we had in the past. So they're not the same numbers, so be careful. So let's say that we're given this data. So here we start low. There's a frequency that we have low, and then this is starting to increase, increase, increase. This is the maximum at this frequency, at this class limit. And then it's going to go down, down, and down. And notice that these are mirrors, 10, 10, 4, 4, 2, 2, and these are in the tails. What do you mean in the tails? Yes, in the endpoints. So I'm gonna start in 014 and then in 90 to 104, up, down, up. So down, up, and then down, and you'll reach a peak at 18. And this is called a normal frequency because you start low, we reach our max, and then we go back down. Any questions on this one? So what are the gaps? The presence of gaps can show us that the data of are from two or more. So why do we even have gaps? You know that we have those class boundaries where they kind of don't interchange, but they might fall under the same class. So be careful. The presence of gaps can show that the data are from two or more different populations. So it could just be out of more than just one, or the converse is not true because data from different populations do not necessarily result in gaps. So you need to be careful the differences. So you can, when you have gaps, it might be from data that can come from different sources, but if they're coming from different sources, that doesn't mean that your data will result in gaps. Okay, just making sure that you understand that. Let's look over here. The table shown is a frequency distribution of grams, randomly selected pennies. Let's look at this. These are represented by gaps and weights. Look at what is the class width? Can somebody tell me what the class width is? What's the difference between 2.5 and 2.4? Isn't that 0.10? Yes. 0.10, this is the class width, okay? This is the frequency. What do we notice? We start high and then we'll go low. We'll have we'll start really high and then go low, low, and then high again, okay? So we'll start at a peak and then we're gonna go down and then we're gonna go up again. But then notice that these are not symmetric. So this is not the same as this or the same as this. So we're gonna have not necessarily a normal, but if we would rearrange it in a way that we will, we can have a 0 and then a 2 and then a 25, so on and so forth. Okay. So the examination of the frequency reveals a large gap between the lightest pennies and the heaviest pennies. This suggests that, so what is the important key? Notice how at first, the weight here is less, and then here, these pennies weigh more than the ones that above. These weigh less. So we have two different contrasts here. We have two different ones, and in the middle, there's 0. Well, what does this kind of tell us? That between, here, they're not telling us they're not giving us the whole spiel of the data, so they're not telling us that there could be pennies made before. So there were before 95% copper, where copper is way more, and then 5% zinc. And then after 1883, now they're 2.5% copper and 97.5% zinc. So this explains the gap between the lightest pennies and the heaviest pennies on the table. So on the top, when they're weighing less, these are the pennies made after 1983. These are the ones before 1983. That's why there's such a large gap. So we have to make sure we know what is our population coming from. Is it coming from because the pennies used to weigh more before? Yes. Okay, our knowledge from before was also going to be taken into play. Okay, So making sure that we understand the big differences, and then here, of course, we will not have something that looks normal because we have two extremities. Any questions? And this is section 2.1. Any questions in 2.1? Okay. We will move on to 2.2. We already went over 2.3. Hopefully you guys remember. We talked about graph that deceived and that enlightened. We covered that last class at the first day of class. So it's just going to be 2.1 and 2.2. And then chapter 3. So let's go to section 2.2. 2.2, a histogram is a cumulative graph of a frequency distribution. So we'll talk about that. What is a key concept? We are going to be, while a frequency distribution is a useful tool to summarize and investigate the distribution of the data, there is an even better tool, which is called the histogram, which is a graph that is easier to interpret than the table of values. So it's actually going to be a visual graph. A histogram consists of bars of equal width, so that this equal width is going to be your class width. The horizontal scale are going to represent your classes of the quantitative data, and the vertical scales will be frequency. So here, this y-axis is going to be the frequency, and the horizontal, your x value, will be your classes. Okay. And we're going to be having different bars in different heights. So the bars and the heights will correspond to the frequency values that we have. So we'll see that in a moment. Any questions so far? In terms of speed, am I going too fast? Is it fine? Let me know on the chat, please. Okay, perfect. So if I'm spinning up a little bit, you're feeling kind of angsty, let me know. So far, so good. Awesome. Okay, so input is always important. All right. What is the important use of a histogram? So visually displays the shape of a distribution. So it will narrate how the visual looks like. Is it a uniform distribution? Is it a normal distribution? What type is it? The shape will tell us. The location, what is the center of the data? Will it have a peak? Will it have a maximum? So these are the questions. Does it have a max? Does it have a peak? All of the things that we want to look at. Is there spread? So is the data have different ranges? So do we have variety? And any outliers? So is there a number that's kind of sticks out? So for example, that's kind of throwing off your data. So if you want to have, let's say that you're having something approximately normal, and then there's an outlier that's kind of throwing you off your data. That makes your data look off. So this is like the strange data. So data that doesn't fit with everything else. That's kind of an outlier. So this is an example of a relative frequent histogram. So this is, again, this is your basic relative. This is your frequency distribution, your basic one that is consisting of your frequency and the commute times. So for this one, it's gonna have your classes here. So if we go back to the example, it has 7, 22, 37. What's the difference between these two? All of this is 15, and then 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 15. These values that you see is your class width. Why are they putting the 7? Because that's just the number that they have here. So in reality, this is from 0. And then here it's going to be through 15, and then from 19, so here we have the 15, and then we have here our 30, and then we will have our 45. So like the ones in the middle, do you see the ones in the middle here? Let me zoom in. Those are your actual, where the lines are. Those are your class sizes. From 0, well, it's actually from 0 to 14. So we'll have we can have our lower class. Let me put that instead. Let me do that. We'll have 15, and then we'll have 30, and then from here to here, 45. And then from here to here, 60, and then from here to here, 75, and then 90, and then 105. Do you see that? Those are in the middle. So they just pick 7 because that's in between, usually in between, or from 0 to 14 on your, on that range on the first one, from 0 to 14, and then from 15 to 29. So the 22 is in between. Does that make sense, everyone? Just trying to be very explicit. Trying to make sure that everybody understands where these 7, the 22, the 37, where are those numbers coming from? It's pretty much half of your lower and upper bounds. Yeah. So you can leave it as is. I usually just put my upper bounds on that one. And then the frequency, how many did we have? From 0 to 14, there were 6 of these. And then from 15 to 29, how many did we have? I think it was 18. And then we had, it looks like 14. And then this one looks like now 4. And then 1 and 1, right? Or is this one, which one's this one? What did we have for the other one? Let's go back to 2, 1. If we go back to our notes, it was 6, 18, 5, 5, 1, 1. So it's 5, 5, 1, 1. Let's go back. So there should be, and look at the height, so be careful. It should be, yeah, that looks about right. That should be 5. So 5, and then 5, and then 1, and then 1. Now that is the frequency, but now the next one is, see how now what changes is the percentages. Instead of having frequencies, your tally, it's going to be your relative frequency, because now that's from 0 to 40. You can actually go on from 0 to 100. And that's so remember the 100 is all the way to 1. So you're tallying up your percentages. So when we have the first one, when we did a relative frequency, this was 6 out of 50, which I believe was at 12%. And then it was 28. And then there was, so going back to the percentage, or we don't even have to. So this is going to be, what we had was 18 over our 50%. So times 100, because we want a percent. And then this is going to be 14 over 50 times 100%. And then this is, of course, the 5 over 15. So this is the 0.10 or 10%, 10%. This one was 2% and 2%. Okay. And that corresponds to what we have. So these are called histograms. This is called a frequency histogram, and the other one is called the relative. This one is the relative frequency histogram. So on your homework, you're not going to be actually doing it, like we're writing it out and doing the whole thing, but they're probably going to say, okay, we'll select, this is going to be a multiple choice question. Can you tell me like which one's the class width, the upper bound, the lower bounds, the limits, so on and so forth. Those, the cumulative. So when we have these histograms, what are we supposed to do with those? We're going to be exploring the data by analyzing the histogram to see what we can learn about CV dot. What is CV dot? We want to find the center of the data, the variation of the data. So the center of the data is usually your mean of the data. the variation, the shape of the distribution, whether there any outliers, and the time. So how long is it? Is it analyzing it by time? So notice here, this is starting low and then it has a peak and then it's gonna low again. So usually right here, this is looking like a maximum. It's gonna have a peak and then it's gonna come back down. Okay, so this is approximately normal. Let's look at the different distribution types. So this is the bell curve. This is a normal. See how it starts low, might peak, and then down, and then we can identify the center. What happens when there's no peak? This is about everyone is usually the same. This is called a uniform distribution. About everyone's the same. This one's skewed to the right because look at the tail. The tail is to the right. And then look over here, the tail on this one, there's more data. This is a left tail or skewed. Let me say that. It's skewed. So see how it's kind of pushed away? This is skewed to the left because look at the tail. The tail starts in the left. So I guide myself when I tell my students how to tell whether something's skewed to the right or skewed to the left. You just look at the tail. So the tail is longer on the left side, so this is called skewed to the left. The tail is longer on the right, so this is skewed to the right. Pretty simple. Okay. So again, this is an example because this histogram. Any questions on the first, these common distribution shapes? Questions here? Okay. So again, this one is my perfectly normal where, see, there's still kind of off by a little bit, but there's a peak somewhere. So it starts low and then it comes increase, increase, it hits a peak and then it goes back down. Okay, this is an example of a histogram. So this is the frequency and these are the classes. See how it's increasing and then going back down. Skewedness, a distribution of center is skewed if it's not symmetric and extends to either one side or the other. If it extends to the left, that's a left tail. If it's skewed to the right, then we would have a right tail, a longer tail on the right. So see how this one is positively skewed because it has a, so look at this. What does it mean to have a longer tail? Well, let's look over here. Look at the data. So it starts low and then it goes up, 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 up. But then look, it goes down, 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 down. But then when we reach the bottom, these are closer and closer. See, look at the differences between, I just want to point out this versus this. There are smaller little details down here that makes this skew to the right down, whereas these are evenly kind of distributed and these are not. Same thing here. When your data up here is starting like very, very low versus the one on your right side, these are skewed to the left because my values down here have a different representation than these. So see how your data kind of moves to the right or moves to the left? So if it moves to the right, it's skewed to the left. It's kind of backwards. And this is another histogram where it kind of does have a peak somewhere, but look at the tail, look at the left. It's starting, there's more starting lower and then it goes up and then down. Okay. Now that is a skewedness. Now, how would we assess normality? Like, how can we tell whether something is normal or not normal? So there is actually a criteria. A criteria will be from a normal quantile plot. So what we do is a quantile plot. How many of you know what that is? A quantile plot is just like pretty much putting your data and then putting dots. That's all it is. So in a normal distribution is the pattern of the points in a normal quantile is reasonably close to a straight line, and points do not show a systematic pattern that is not a straight line pattern. So when you are looking at a normal quantile plot, you should have something that goes to a straight line. So you would have to reorder your data from lowest to greatest and then check if it's normal. What would be a not criteria? Let's say that we have a population, they're not normal, meaning that they do not have a straight line. So for example, if I give you data and let's say my lines are all kind of scattered all over the place, this doesn't have any data whatsoever. It doesn't follow any systematic pattern. It's not reasonable close and it does not have a reasonable pattern. So you can have this, or if we have another one, let's say it looks like this, or let me see, let me change it. So this one doesn't have, these are kind of scattered all over. So this one's no systematic pattern. So that would be the second one. But what if we have something like that looks like this? See how this is not a line? This would be more like of a parabolic curve. That's what this is saying. So it's not line or reasonable, it's not a straight line pattern. It might look like something else. It might look like a parabola, like an exponential, like a logarithm. Something that is not a straight line. So then that way you will not have something that looks normal. So this is an example. This is a normal curve because notice that your points are reasonably going up. They have some pattern. They are reasonable close to each other. And there's no systematic pattern that is not a straight line pattern. This is actually a straight line pattern. So this qualifies to be something normal. So we're going to see some examples next. Look at this. See how your graph looks like, this looks like a logarithm, an exponential, and look, yeah, it definitely looks like a logarithm from in terms of mine. So this is not, these points do not lie to a reasonable close pattern. See how it's all of your data kind of lies right here, and then it's starting to go increase, but you start down here. This is not normal. So this is look like a logarithmic type of curve. Now this one, why is this not normal? You have to look at the peak and say, oh, well, yeah, but no, because look, it goes up, then it goes down, and then it goes up. So see there, do you see that there's a curvature here? So some points are above, some points are below. So this shows a systematic pattern, but it's not a straight line pattern. It's actually, it has curve. It looks like a cubic. So it goes up and then down and then up again. So this has curvature. So this is a systematic pattern, but it's not a straight line pattern. So this is not a normal. And that is it, section 2.2. So 2.1, it was a frequency distribution, cumulative distribution, and relative frequency. Section 2.2 is actually the visual representation. It's called a histogram. We looked at skewedness to the left, and skewedness to the right. And what does it mean to be normal? Do we have any questions so far? How do you guys feel in terms of the time, the speed, the comprehension? Everything's fine? Everything's falling into play? So pretty much, what you guys have to do next is your homework, making sure that you understand your homework. And you're able to demonstrate that as you moving forward, you're understanding the content. That's what I care about. So that is 2.1 and 2.2. I'm going to pause this recording and then I'm just gonna stop it for recording purposes and then I'll start a new one.